equations there, what you get is what the question is asking you. The question is asking you, what's the enthalpy change for this reaction? Well, if you add the matter side of the chemical reaction together, you end up with the overall reaction. What are you going to do with the energy aspect of the reaction? Well, you simply add these two numbers together. So negative 187 plus 0.6 plus 95.4. That will give you the enthalpy there, negative 92.2 kilojoules. So you're simply adding these two numbers together as well. Always treat the energy as part of the reaction. Here you add all the matters together. Everything on the left side still stays on the left side. Everything on the right side stays on the right side. If you have same item, same quantity of the same chemical on both sides, they cancel out. If you have two of the same, 2 moles of the one particular chemical on the left side of the equation and 3 moles of the same chemical on the other side, well, 3 minus 2. You have 1 left on the right. You have none on the left. So you're doing a simple addition here. So when you do state function calculations there, when you use Hess law, we may give you a question that's quite confusing, asking you for the enthalpy of this particular reaction, giving you these information. More than likely, every time you see a question like that, it's just a matter of adding things together. And sometimes it may even involve reversing a reaction. So we will give an example of reversing the reaction there. Now, one thing about reversing the reaction, if this reaction, the first one, okay, if the first reaction, hydrogen plus N2, nitrogen give you N2H4, if this is an endothermic process, and if you reverse it, the reverse process is going to be exothermic. The amount of energy is simply, well, the energy stays the same. The amount of energy is the same. You just change the sign. Positive sign here for the reaction going from left to right. And if you reverse it, going from this N2H4 to 2H2 and N2, it's going to be negative 95.4. So that's something that you need to keep in mind. And again, I understand, I mean, when that question that one of my afternoon class students asked me, how did you learn chemistry? What was your experience when you were in college, when you studied chemistry there? Well, this part is actually quite confusing. When you look at the equations there, and sometimes you have to reverse the direction of the reaction, trying to figure out numbers there. But one thing you need to keep in mind is that, and it may appear confusing to you right now, but the thing here is that the Hess law basically says, if you need to figure out the enthalpy change for an overall reaction, you have multiple steps involved in that reaction. All you need to do is to add them together. Matters added together, energy added together. So this is what we have here, and then giving you probably a more visual diagram there. Going from hydrogen, nitrogen gas to N2H4, that's an endothermic process. So step 1 requires energy. And then when you have N2H4, you put more hydrogen gas in there and forming NH3, 2NH3 there. Well, that overall process releases energy. It's an exothermic reaction. The net difference is the difference between the green arrow and the red arrow. Red arrow is a positive number, green arrow is a negative number. So the overall process, you end up with a negative number here. Negative means exothermic. Now, if it so happens the green arrow is smaller than the red arrow, then the overall process is going to be endothermic. So it's a simple arithmetic there. Positive number, negative number, you're just adding numbers together. And when you end up with a negative sign, you know the overall process is going to be exothermic. And when you end up with a positive number there, well, you know the overall process is going to be endothermic. So that's something that you need to keep in mind. Okay, so that's what Hess law is all about. And now we want to use Hess law in the last learning objective in this particular chapter. We want to use Hess law to do some calculation. We're going to give you some examples of doing the calculation. Remember, energy is a state function. When you try to figure out the overall energy requirement for particular physical chemical processes there, all you need to do is to add things together. Reactant side, you add them together. Product side, you add them together. When you do that, there's always a way you will figure it out. The overall reaction is the result of the addition here. Now, sometimes, though, you may need to reverse the given information, the direction of the chemical reaction as a given information there, you may need to reverse it. And we're going to take a look at the an example in the last learning objective. Now, one thing that we do want to point out here is that for all of the matters that we know of, the enthalpy of formation, or the molar enthalpy of formation, has been measured and documented in a handbook. CRC handbook for chemistry and physics. It's about this thick, and pretty much anything that you need to know about a particular compound or an element has been measured and documented in that handbook. So the molar enthalpy of formation is the amount of energy either absorbed or released when 1 mole of that compound, or 1 mole of the matter, I don't want to use the term compound, but when 1 mole of the matter is formed from its elemental state in their standard, from its element in their standard state. Now the standard state, this is different from what we call STP in the gas law chapter, there in chapter 5. The standard state refers to the most stable form of an element in the physical state in which it exists at 1 bar. 1 bar refers to the pressure. The pressure is about 1 atm, 0.9869 atm, and the specified temperature. And the temperature can be 20 degrees, can be 25 degrees. So when you look at that CRC handbook for chemistry and physics there, you always see on top of each table there's an indication of the temperature. What is the temperature that we use to measure these different things there for all these different quantities there? So the most stable form of an element in the physical state in which it exists at 1 bar, well, hydrogen, the most stable form, most stable form of that element in the physical state is a gas. Hydrogen is a gas. Oxygen is a gas. Okay, and if you form a reacting hydrogen and oxygen together, you get water. And the standard molar enthalpy of formation of water, most stable form of, well, we're talking about the standard state from its elements there. For a compound, though, the standard state, the most stable form would be at room temperature, somewhere around 20, 25 degrees Celsius. The water is a liquid. Okay? So how much energy is released when 1 mole of water is formed? That's how we define molar enthalpy of formation. Well, molar anything is about that quantity in 1 mole of chemical. Okay? And just like the molar mass, the mass in grams or 8 mole of chemical. Molar volume, number of moles, the number of liters occupied by a particular gas under standard condition. On molar enthalpy, the amount of energy released released or absorbed when 1 mole of that substance is formed. Okay, so in this case, and then this is the table, part of the table in your textbook there, and it gives you, for the elements there, the standard enthalpy of formation for element would always be 0. Okay, for, well, the elements in its most stable form. Bromine is a diatomic molecule. You do not have single bromine atom exist in nature. When bromine exists in nature, it actually combines 2 bromine atoms combined together, they form a bromine molecule, Br2. Br2, the most stable state, physical state at 1 bar, is a liquid. So bromine,